Welcome to qnawire.
The Saha equation does with ions what the Boltzmann equation does with energy levels. That is, it uses a statistical distribution um, on energies for particles and determines how much of one type of ion is able to coexist inside of a gas compared to other states of the ion. Uh, so let's write down the Saha equation. It says that the I plus one-th state of ionization, that means one more electron removed than the number below I, times the number density of electrons in the gas, so how many are already free, can affect whether ionization is easy or difficult. But that is equal to 2 over the thermal de Broglie wavelength cubed. Okay, so we'll call that thermal. And then we have the degeneracy of the ion compared to the degeneracy of the one less electron removed ion. And here comes the Boltzmann factor, as they call it. So what we're going to take is the difference in ionization energies between those two states and compare it to the available thermal energy in the ensemble. And that is the Boltzmann's constant times temperature. Okay, so a lot to parse, but the number density of electrons can be found from the pressure. So remember that we have an ideal gas, so the electrons are behaving fairly much like an ideal gas, we assume, at the densities. So pressure times volume equals nkb times temperature, n being the number of particles. So the pressure of the electron gas is Ne kb times T. So we could find the number density if we knew the electron pressure. And what we'll be doing is using this equation inside the sun. So we know very well what the electron pressure is, as well as the average, the temperature. The thermal de Broglie wavelength comes from the distribution in momentum, and of course, taking the thermal momentum in the ensemble, we can determine that thermal wavelength. Okay, so rather difficult to derive this equation. We'll just take it as given. And what we are going to be doing with this is we are going to be looking in the sun, trying to determine how much hydrogen negative ion there is compared to hydrogen neutral, which is sometimes called H1. Let me write that the way I should, H with a Roman numeral. So this is the hydride ion, and H1 is neutral hydrogen. It turns out that the hydride ion is quite important in cooler stars. It turns out that it does a fair bit of contributing to the opacity of the star. So here, what we are going to be doing is looking at the degeneracy, of course, between the hydride ion. So let's just kind of draw what that would look like. There's a proton and 2 electrons. We'll put them in the 1s state, and they must go in with opposite spins. Okay, so there's only one possible way to arrange them. So G, we'll call it, to call that G minus, is equal to 1. Whereas, of course, in the neutral hydrogen atom, we have just one electron, and it can either go in a state with the spin up or the spin down. So the degeneracy of the neutral atom is 2. Okay, so let's arrange our equation. There's some things to find out. We are well aware that the pressure, electron pressure, is about 1 Pascal. We'll call it 1.5 newtons per meter squared. And we can then determine the number density is 1.5, Boltzmann constant 1.38 times 10 to the minus 23 joules per Kelvin. And then we have the temperature in Kelvin, 5780. And yeah, that should be in terms of number per cubic meter. Okay, just thinking about the units a little bit with joules and newtons and whatnot. And this turns out to be 1.88 times 10 to the 19th per cubic meter, which sounds like quite a lot, but it really is not such a big deal. They aren't squeezed tightly into the gas. The thermal de Broglie wavelength, let's go ahead and find that as well. So we have h over the square root of 2 pi. Let's just put in some numbers here. H is, of course, Planck's constant, 6.63 times 10 to the minus 34. And this will come out in meters times 2 pi times the mass of the electron, 9.11 times 10 to the minus 31 kilograms, Boltzmann's constant, and the temperature one more time. Yeah, Kb times temperature is going to show quite a lot in this calculation. And we'll at some point want it in electron volts, as we'll see, but not a big deal. And this is of the order of 1 nanometer. Interesting. Okay, so now I think we're ready to calculate the ratio. The only thing that we need is that difference in ionization, and it sort of depends how we are going to write the ratio. So I will write it as intended, putting the higher positive state on top of the negative state. And so we'll call this N1 for hydrogen 1 over N minus is the ratio that we'll be finding. And let's see, this is 1 over the wavelength cubed, thermal wavelength cubed. We're going to put in the degeneracy, 2 over 1 times 2. There's a factor of 2 already in the equation. And so the only thing we need is the difference in ionization energies. And of course, they're both in hydrogen, so you would think they would both be around 13.6 electron volts. And so what we're going to put in is that once you put that extra electron into the atom, the extra electron will make the H minus easier to ionize than H neutral. And the difference is what is called the electron affinity. Okay. Which is basically the energy the atom, the electron loses by falling into the atom. Okay, so that's what we'll put for our difference, is the electron affinity for hydrogen. And looking that up, so there's different ways to look it up, but that is equal to 0.755 electron volts. So yeah, we'll get the kBt in terms of electron volts, and working that out, kB times T is going to be 8 times 10 to the minus 20 joules. We've already done that calculation a bunch of times, divided by 1.6 times 10 to the minus 19 joules per EV, and that's about half an EV. Okay, so that exponential factor is going to be quite small, minus 0.755 divided by a half. Okay, so working that out, it gets to be a little bit of a mess. The de Broglie wavelength combined with the NE. So let's just write this down. N1 over N minus is about 1.06 times 10 to the 27th is the factor out in front. Oh, there's a factor of 4 from the degeneracies, and the factor of 2 that's already there. And then divide by 10 to the 19th, which is the number, electron number density. And then the exponential factor is about 0.22. And this comes out to be about 5 times 10 to the 7th. So yes, there aren't that many hydrogen ions, minus ions, compared to the neutral state. But because there's a lot of gas there, they can make a big difference in how the star behaves.